So the formula for discharge through a Francis turbine. So this formula we can write by neglecting the effect of thickness of the runner blades. So here I have put one assumption that I am going to neglect the thickness of runner blades. Okay. So I write Q, that is the discharge. This is equal to the area of flow multiplied by the velocity of flow. So this is equal to, now the area of flow I can write the circumference of runner multiplied by width and multiplied by the velocity of flow. Okay. Now the circumference I can write as pi d. Width of the runner I can write it as b, and the velocity of flow that I can write as vf. Okay. So discharge, the formula I can write as pi db into vf. So where d is the diameter of the runner, b is width of the runner, and vf is the flow, or you can say the velocity of flow, okay, or flow component of velocity. So that give you the formula for discharge. Now next is how we select the velocity triangle. So for this we see outlet velocity triangle first. So next I see how to select outlet velocity triangle. As we all seen earlier that the where we have three different shapes for outlet velocity triangles depending upon angle alpha O. So if I see this diagram, so in this diagram you can see three different shapes of velocity triangle. So here in the first you can see angle alpha O is less than 90 degree. Okay. So here alpha O is equal to 90 degree, and in third alpha O is greater than 90 degree. So at outlet we have three different shapes of velocity triangle. Okay. Now this velocity is VO. Okay. And this component is VWO. So here the component VWO is equal to 0. Okay. So now you can see, now the kinetic energy of outgoing water is given by VO square divided by 2. This is the kinetic energy per unit mass of water that is leaving the turbine. So this is with respect to absolute velocity at the outlet, that is VO. So I can write that kinetic energy of leaving water as VO square divided by 2, and this is the kinetic energy per unit mass. Okay. So as we know that this leaving energy is just a wastage of energy that going out from the turbine. So our purpose is to minimize this waste energy or leaving energy. So we have to minimize it. So to minimize this energy, you can see from this formula that we have to reduce the value of VO. Now you can see out of these three triangles, this is the one triangle, this is the second triangle, and this is the third velocity triangle at the outlet. Now you can see out of these three, for which triangle VO is minimum. So now you can see in second triangle, that is this one, when angle alpha O is equal to 90 degree. So in this case, VO is minimum as compared to VO in triangle 1 and VO in triangle 3. Okay. So you can say it is desired to keep this value to minimum. So from the outlet velocity triangle, it can be observed that the velocity VO will be minimum when angle alpha O is equal to 90 degree. Okay. So in that case, VO coincides with VFO. You can see here VO coincides with VFO. Okay. Now further in this velocity triangle, you can see VWO, world component of velocity, is 0. VWO is 0. Okay. So thus in practice, all the reaction turbines are usually designed for this radial flow. That means the angle alpha O is equal to 90 degree. So for the outlet, we have this velocity triangle. Sorry. Okay. So to minimize the value of VO, I have to select the second velocity triangle when angle alpha O is equal to 90 degree. Now further in second triangle, you can see we can further reduce the value of VO if we reduce the value of beta O. Okay. So this angle is also kept small, that is in the range of 15 degrees. Okay. So keeping these two consideration in mind, that for outlet velocity triangle, the first condition alpha O equal to 90 degree, and then beta O is minimum, that is approximately equal to 15 degrees. So we have the second velocity triangle at the outlet of the Francis turbine. Now further in this, you can see VWO is equal to 0. Okay. So this we also call as the radial discharge of a turbine. Okay. So that means for radial discharge, we can kept alpha angle equal to 90 degree, or you can say VWO equal to 0. Okay. Now, this also implies that the direction of the absolute velocity of water, you can also note down that the direction of the absolute, you can say the direction of VO, that is the absolute velocity at the outlet, is perpendicular to that of the tangential velocity. Okay, so that is u. So tangential velocity at outlet, I can write it as uo. Okay, so vo is, you can see here, vo is, this is vo, this is perpendicular to u or uo. Okay, then you see, now this is the outlet velocity triangle. Now next we see the complete velocity triangles, that is at the inlet as well as at the outlet. Now at the outlet we have always the triangle with angle alpha O equal to 90 degree, but now at the inlet we have different shapes of velocity triangle that depends on the specific speed. So depending upon the range of specific speed, we have different shape of velocity triangle at the inlet. Now we see the complete velocity triangle. Now the first one, you can see here. Now this is the velocity triangle for the range of specific speed ns equal to 50 to 100. That is for slow runner. Okay, so here, okay, then we have this VRI. Okay, this velocity is UI. Okay, and then we have VWI, this one. Okay, and this is VFI. We have two angles, angle 1, alpha I, and this angle is beta I. So, depending upon the angle beta I, we have now the different shapes of velocity triangle at the inlet. So here in this diagram, beta I is less than 90 degree. Okay, beta I is less than 90 degree, or at the outlet now you can see we have the velocity triangle with angle alpha O equal to 90 degree. Okay, that is alpha O equal to 90 degree. So you can see here, now this direction of VO, this is normal to or perpendicular to UO and always directed toward the center of the runner. Okay, so that is the meaning of radial discharge, alpha O equal to 90 degree at the outlet, you can say. Now the second velocity triangle, for medium speed runner, for this the range is 100 to 150 for specific speed. So NS is 100 to 150 and this is the medium speed runner. Or you can see here the angle beta I equal to 90 degree. Okay, and also the angle alpha O equal to 90 degree at the outlet. So this is the second shape of velocity triangle. Then the third one, you can see the third one, that is for fast runner. The range of specific speed is 150 to 250. Okay, so here you can see angle beta I is greater than 90 degree at inlet, and at outlet angle alpha O equal to 90 degree, and further VO, that is also equal to VFO, is directed towards this center. Okay, fourth one, that is for more high value of specific speed, that is normally for axial turbine, not for this case, but you can see that velocity triangle also. Okay, you can see this one. So this is for specific speed range 250 to 850. Okay, and this is for axial flow runners. So that is for higher value of beta I. And again, angle alpha O equal to 90 degree at the outlet. So this shape of velocity triangle is usually we have for axial flow runner. However, these three shapes, the third one, the second one, and the first one. So here angle beta I is less than 90 degree. So these three are for Francis turbine. Okay. Now the formula for specific speed, we have already written that. So that you can note down as NS equal to N under root of P H raised to power 5 by 4. Okay. So N is the speed of the runner. So that is in RPM. Okay. So P is the power produced. So that we use in kilowatt. And H is the net head, that is in meter. Okay, so you can see how the shape of velocity triangle for Francis turbine depends on specific speed.